Let's construct a group of order 2. So the set contains just 2 elements. One element has to be the identity, so we call it E, and the other element let's call A, so that it has a name. And now let's write down the group table for this group. EA, EA. We know identity times something gives something, so there has to be an, let's use a different color, there has to be an E, and an A, and an A here. And now since every element appears exactly once in each row and each column, there has to be an E here, no other choice. So this is up to renaming the elements of this group. This is the unique group of order 2. Of course it can come in many different guises. Think for example of Z2. That would be the set, it's just the numbers 0 and 1, and the operation would be addition modulo 2. Now what's the group table in this case? 0, 1, 0, 1. Let's draw a group table. 0 plus 0 is 0, 0 plus 1 is 1, 1 plus 0 is 1. I wanted to use different color inside here so that you have the labels, and then the table itself is the orange stuff and the pink stuff above. And now 1 plus 1 is 2, but that's the same as 0 modulo 2. So this is the same group table as above, but we just called the group elements differently. Here's another way to write down this group. Let's say the group elements are these diagrams here. Diagrams that connect 2 points on the left, 2 points on the right. Same here. And I only care about which orange point is connected to which pink point, not how they are entangled and crossing each other and so on. So let's say this would be the same as this diagram, and even this diagram would be considered the same as the diagram in the middle. Now, what shall be the group operation? If we take these 2 group elements and we multiply them, and we want to just join the lines here in the middle. So we would get something that looks like this, which is of course, by just twisting a bit or moving the point where they cross, is the same as the second group element. If I multiply, for example, this second group element with itself, we get this picture here, which is just the same as the first group element. And now we can also draw a group table. Our group elements are these diagrams. And we see that the first diagram is the identity, because multiplying it with this crossing diagram gives just this crossing diagram, and the crossing diagram times itself gives the identity. So this is another instance of a group with 2 elements, and the group table of course looks the same as the previous group tables, just different names for the group elements. It's not all. We can come up with more examples. Let's say we consider functions, complex valued functions, let's say from Rn. Rn to C. And now we consider some linear operators. OE shall be the operator acting on F, so OE on F gives us another function of n variables. And if I evaluate OE on F at the position x, then I get back just f of x. And here's second operator, OP, acting on F. If I evaluate that at x, I get f of minus x. And now we see if we apply this OP thing twice, we get two minus signs, so we come back to f of x. So OP acting on f, and then OP acting on the result, the whole thing evaluated at x, is f of x, which means that OE after OE, OP after OP is just OE. And now we can draw the group table again. So our group elements are OE, OP, OE, OP, and we get OE, OP, OP, and OE. Same group table as above, but now the entries are not numbers, not diagrams, not some abstract things, but in this case linear operators acting on some vector space here. And one last example. Let's consider once more functions of, say, two variables, each in Rn. So we go from Rn times Rn into the complex numbers, say, doesn't matter. And now OE shall be the operator when acting on x and evaluated at x1, x2. Sorry, acting on psi evaluated at x1, x2 gives us psi of x2, no, psi of x1, x2. So OE will be the identity thing in our group again. And now second operator OS acting on psi evaluated as at x1, x2. This will be psi of x2, x1. So we exchange the two elements, the two arguments in the function psi. And of course, if we exchange them again, then we are back here. So OS squared is just OE. And once more, we have this group table. OE, OS, OE, OS, the labels for lines and columns, and the entries are OE, OS, OS, and OS squared is OE. So 5 groups with 2 elements, which are all isomorphic. And later we will consider some of these isomorphic groups, not as groups themselves, but we will consider them as representations of some of the other groups that I haven't defined yet, so that's for later.